Today's lesson is on extrema and average rate of change. First, we're going to start talking about increasing and decreasing intervals. We spent a lot of time on this in Algebra 2, so hopefully it's just a review. For increasing and decreasing, we're going to use interval notation. And inside this box right here, it's just a helpful graphic to help you kind of visualize what increasing and decreasing intervals are. So I had mentioned that we're going to think of an ant climbing on a graph, and the graph is going to climb from left to right, so it's always going to start on the left side of the graph. And then right here, this is the important part. So if the ant is climbing uphill, it would be an increasing interval. If the ant is climbing downhill, then it would be decreasing. And if it's on a flat surface, then it's constant. One of the biggest things to remember when you are doing increasing and decreasing is that you use x values only. And you actually write it with interval notation. So x values and interval notation. Using x values always throws everyone off because the graph is increasing and decreasing on the y-axis. That's why it looks like it's going up or down. But then we're choosing to write the interval with the x value. It's just standard form. It's how we do it. So make sure you pay attention. I'll use a highlighter to indicate where it's increasing and decreasing and then why we're using the x value. All right, for number 1, we have quite a bit going on here. You can see the graph changes directions multiple times. If we make a few marks, if we start over here on the left side of the graph, we're starting at negative infinity, typically, and we're moving towards positive infinity. So again, we're starting on the left side of the graph. In this example, we are going to start right here. We're going to head down until this point. Then we start to head back up until this point. We have a constant interval where we would be walking on flat ground until there. And then we start to head back down until this point. Okay, so this graph has a starting point and an ending point. We can see it clearly starts right here and it ends right here. So we need to list all of our intervals between those 2 points. And once again, we are using x values only. So at these turning points, I'm going to highlight the turning point and I'm going to highlight the x value. Okay, quick note. Notice that I didn't mark this point. That's because that is on this interval that's increasing. A line is made up of infinitely many points, so even though that one's marked, it doesn't have any use for us in this example. It's in the middle of an increasing interval, so we do not have to worry about that point. This point is not helpful. All right, starting on the left, right here, we are decreasing from -6 to -4. At -4, we increase until this point, highlighted in purple, and that's until 0. We are increasing from -4 to 0. At 0, we have a constant interval until the x value of 3. And at 3, we head back downhill until 6. That's our last decreasing interval, from 3 to 6. All right, please note that you use parentheses for all increasing and decreasing intervals. You never use square brackets because at these turning points, You cannot indicate whether it is increasing or decreasing at that point, so it cannot be included. It is a turning point. It's where the graph changes direction, so we do not include it. That means parentheses for every interval. Also, don't forget your unions. If you have multiple intervals, connect those with unions. Okay, number 2. I'm going to do the same thing here. We're going to just start on the left side of the graph. We're going to mark that we're going uphill. Then we have a constant interval. Then we're going uphill again. Then we change and head downhill. I'm going to highlight the starting point, the ending point, and the actual turning points. Right here we have a starting point at an x value of -3. Here we have a turning point. It's changing direction from increasing to constant at an x value of -2. Right here we have a change from constant to increasing at x value 0. We have a change from increasing to decreasing at an x value of 2, and the graph stops at 3. On the left side of the graph, we're going to start with an increasing interval from -3 to -2. We have a constant interval from x value -2 to 0. We have another increasing interval from 0 to +2. And we end with a decreasing interval from 2 to 3. Again, these are written in interval notation, so please do not mix these up with ordered pairs. These are actually intervals of either increasing, decreasing, or constant parts of the graph. Okay, I'm gonna do one more in this on your own section, and then I'll leave the last one for you. But the reason why I want to go over number 1 is because this graph has ends that continue forever. So we're going to be using negative and positive infinity here. For this first graph, we are starting at negative infinity and we are increasing until our turning point where we stop and we remain constant until positive infinity, or I should say forever. Right here is our turning point, and that point is not marked for us, but we can see that the x value is at -3. So we have an increasing interval from negative infinity to -3. At -3, for an x value, it changes direction. At that point, it becomes a constant interval from -3 to positive infinity. Next, we're going to talk about extrema, which are critical points at which a function changes its increasing or decreasing behavior. That means it changes direction in the coordinate plane. So we're specifically going to call this local maxima and local minima, and those are both plural because you can have multiples on each graph. So functions can have hills and valleys, or places where they reach a minimum or maximum value. It may not be the minimum or maximum for the whole function, but it locally is going to be either one. So it's locally either the max or locally the min. So basically what it's saying is if you have a high point or a low point, you're going to call it a local max, you're going to call it a local min, whichever one it applies to. If we take a look at this sample I have for you, you can see that this right here is going to be the high point on this curve. So we call that a local max. On this curve, we have a low point. We're going to call that a local min. And on this curve, we have a high point. We call that a local max. If we look at our first example, we have 3 points that stand out to me. So we're going to have what appears to be 2 local minimums and 1 local max. Okay, when we list our extrema or local mins and local maxes, we're specifically looking for the y value. The y value or something on the y-axis would be the height of the point, so how high or how low the point is. So it would make sense to be listing the y value, seeing that is, how high or how low the point goes. But most of the time, you'll see that I write it as a point and then I circle the y coordinate just so I know exactly where I'm looking at. So for example, for the local min, I'm going to write the first one as -1, 1. And then I'm just going to indicate that this value right here is the actual minimum value. Now I could write that out. I could write we have a minimum value of 1 occurring at the x value of -1, but I feel like that's a lot longer than just indicating what the point is and then indicating what the minimum value is. The other minimum value is happening at 3, 0. So 0 is our minimum value. All right, we specifically have a local min at 1 and 0. All right, for local max, that point occurs at 1, 2. 2 being the actual height, so that's going to be the max value. So we could say that we have a local max at 2. And that's it. So just really what the point of this is just making sure you understand if you have a high or a low point on the graph. Okay, so next we're going to take a look at average rate of change. And the average rate of change is when you're looking at a line like this one here. Actually, I should say you're looking at 2 points on a graph and you're connecting them with a line to get that average rate of change between the 2 points. I'm going to switch and watch a short clip of a YouTube video to explain what the average rate of change is doing or what we're getting at and what we can use it for in real life.
In calculus, we'll be working with many different types of functions. One of the major things we'll be interested in is how these functions change. Fortunately, this idea is very intuitive, and you may have started to do this already in previous math courses. Let's take a look at a quick example to see how we do this. If we read a function from left to right, we can see that sometimes it increases and other times it decreases. I like to imagine the function as a roller coaster so that I can easily see places where it is going up versus where it is going down. Knowing how a function increases and decreases certainly tells us more about the behaviors of a function, but it's still not precise enough for what we will need later. To see why, let's look at 2 more functions. Here are 2 functions that are both increasing, but one is increasing more rapidly. After all, it looks steeper. But how steep is it? Where does it increase the most? From these questions, you can see we need some way to describe how rapidly the function is increasing or decreasing, so we can better compare their behavior. So let's take a step back. If these 2 functions were lines, this would be a much easier problem. When we are working with lines, we can use the notion of slope to accurately describe how quickly a line is increasing or decreasing. This comes from measuring the rise of the function in the y direction versus the run of the function in the x direction. With slope, we can say how much it is increasing or decreasing by simply giving this ratio of numbers. So we can say that the line on the right is increasing more simply because it has a larger value for its slope. Now back to our functions. These functions are definitely not lines. So unfortunately, we can't use the idea of slope to describe how they're changing. Or can we? To build a line, all we need are 2 points. If we choose 2 points on our function, then we can certainly draw a line right through them. Note how the line works as a good approximation when describing how the function is changing. If the line we draw is steep, then we can expect that our function is increasing fairly quickly as well. But it's only an approximation right now. If we change the 2 points we are using, we will get a different value for the slope of the line. What this line really tells us then is the average change of the function. How much the function has changed in the y direction versus the x direction between the two given points. Let's play around with this idea so that it makes a bit more sense. Suppose we choose 2 points on a function. Drawing our line like earlier, we can find it has a slope of 2/3. This tells us that as we are moving on the function between the 2 points, we may go up, we may go down, but on average we'll increase in the y direction by 2 as we move in the x direction by 3. Or maybe a better way to say this is the average change of the function between the 2 points is also 2/3. If we choose 2 other points, our line is now horizontal. This has a slope of 0. If we move along the function now, you'll notice that despite the ups and downs, we'll end up at the other point at the same y value. So on average, there is no change in the function. So by describing the slope of a line between 2 points on a function, we can get a lot of information about the behavior, specifically its average rate of change. Depending on what the function describes, this could give us information like the average speed of a car or the average flow rate from a tank of water. The possibilities are endless.
So the average rate of change between any 2 points on a graph is the slope of the line through the points. We're going to calculate this by the change in y divided by the change in x. Specifically, we're going to evaluate the function at one of the x values and also at the other x value. So if I just scroll down, let's label this one as x sub 1 and x sub 2. We have 2 x values here. We have x sub 1 that's equal to 1, and we have x sub 2 that's equal to 3. So just as a reference, what you're going to do is you're going to evaluate the function for the second x value, whatever your answer is. You're going to use that. Then you're going to evaluate the function for the first x value. Subtract your answer from the first one you found. You're going to divide this by just the x value of the second point minus the x value of the first point. Let's take a look at this first problem. For number 1, we're using the function f of x is equal to negative x squared. So we are going to use the equation with x sub 2, which is equal to 3, and x sub 1, which is equal to 1. Before I calculate the change in y divided by the change in x, I'm going to evaluate the function at 3, which gives me negative 3 squared, which is negative 9. So I know that f of 3 is evaluated at negative 9. Next, I'm going to find f of 1. That's equal to negative 1 in parentheses squared, which is equal to negative 1. Therefore, the function evaluated at 1 is negative 1. Now I'm going to use my equation, the change in y divided by the change in x, which is specifically f of x sub 2, we just calculated that as 9, minus f of x sub 1, which we calculated as negative 1, divided by x sub 2 minus x sub 1. All right, that's just the equation. that we're filling in. So if we actually fill that in, we know that f of x sub 2 is equal to -9. We know that f of x sub 1 is equal to negative 1. We're going to divide this by x sub 2, which is 3, minus x sub 1, which is 1. -9 minus -1 is the same as adding. That gives us -8. -3 minus 1 is 2. So -8 divided by 2 is equal to -4. -4 is your answer. So the average rate of change from 1 to 3 on the equation f of x is equal to -x squared is equal to -4. All right, the second part is the same type of equation, but I wrote it a little bit different, which you will see probably more often actually. This is an interval notation, and it's asking you from the interval of -2 to 8. So we have x sub 1 x sub 1 is equal to -2, and x sub 2 is 8. We're using the same function as before. Let's evaluate the function at 8. That's going to be -8 squared, which is equal to 64, or -64, sorry, -64. And f evaluated at -2 is equal to -2 squared. -2 squared is +4, but we still have this negative sign. So this is equal to -4. Okay, we know that the change in y divided by the change in x is equal to f of x sub 2, which we calculated as -64, minus f of x sub 1, which is -4, divided by x sub 2, 8, minus x sub 1, or -2. -64 minus -4 is the same as adding, leaving us with -60, divided by -8 minus -2. Sorry, that's +8 minus -2 is +10. This simplifies to -6. -6 is your final answer. That is the average rate of change between -2 and 8 when using the function f of x is equal to -x squared. And lastly, we have a real world problem. So we're looking for the average speed here. The problem says that the height of an object that is thrown straight up from a height of 4 feet above the ground is given by h of t is equal to -16 t squared plus 30t plus 4, where t is the time in seconds after the object is thrown. Find and interpret the average speed of the object from 1.25 to 1.75 seconds. So I'm going to highlight the equation. Obviously, we need to use this to evaluate our function. I'm also going to highlight right here is x sub 1, right there 1.75, x sub 2. We're going to evaluate the function. H of t is equal to -16 t squared plus 30 times t plus 4. You're going to want to use a calculator for these ones as well. When we evaluate it at x sub 2, we're going to start with that one. We evaluate h at 1.75. That means we're going to use our calculator and we're going to type in negative 16 parentheses 1.75 squared plus 30 open parentheses times 1.75, and then we have plus 4. When we evaluate that, we end up with the answer of 7.5, and you should all check that in your calculator. When we evaluate the function at x sub 1 or 1.25, we're going to have negative 16 times 1.25 squared plus 30 times 1.25 plus 4, which gives us an output of 16.5. All right, now that I have my two, the function evaluated with my two values, I know that the first one is f of x sub 2, the second one is f of x sub 1. I can substitute these into the equation and I can solve. I'm going to have 7.5 minus 16.5 divided by 1.75 minus 1.25. 7.5 minus 16.5 comes out to negative 9. 1.75 minus 1.25 is 0.5. Negative 9 divided by 0.5 is equal to negative 18. Negative 18 is your average rate of change. That is your answer. If you were to interpret your solution here, you would have to think of this as the slope. So if we think of this as the slope or change of y over change of x, we would have our answer of negative 18. But we don't have a denominator there, so just remember that anytime you don't see a denominator, it's over 1. The change in y, or the variable y, in this particular example represents the height. So the y-axis over here represents the height the object is at. And the x-axis, it says it up here in the description, is time in seconds. So what this is telling us is that the change in y, or negative 18, means the object is falling at a rate of 18 feet per second. So 18 feet being your numerator, 18 feet, and per second, or 1 second, being your denominator. Again, the y variable represents height, the x variable represents time, so that object is falling 18 feet per second.